Okay, so thanks for coming. Let's get started with the session. So in this talk, I'll be talking about application integration in the cloud native and microservices landscape. So if you look at the title, we have quite a lot of buzzword covered in the title. But my objective is to talk about one of the very important concept in building cloud native applications, the application integration, which is not discussed that much in the enterprise, right? So brief introduction about myself. I'm working as the Director of Integration Architect at WSO2, and also I authored a book on microservices architecture, microservices for enterprises, and also working as the Product Manager of WSO2 Enterprise Integrator. And I closely work with most of the Bay Area communities on microservices, APIs, and integration. So this talk contains most of the insights on how integration is changing and how microservices architecture is changing with the modern enterprise needs. So the title is about building cloud native applications and the role of application integration, right? So before moving any further, let's look at what is cloud native. So if I ask you any questions, like any question related to cloud native, you would probably say cloud native is building applications, leveraging the cloud or deploying into the cloud. But at the heart of cloud native architecture, there are four main principles, right? So a given cloud native application comprises of a given set of microservices, right? A cloud native application is a combination of set of microservices or serverless functions. And those functions or microservices are packaged into containers. So that's where Docker and Kubernetes are coming into the picture. So once you package them into Docker and Kubernetes, then you run those services on top of a continuous delivery model. So that means you develop your service, you test, you write tests, you write whatever the integration test, and you create a flawless experience from dev to production and fully automate that process. So that's where all the GTOPS and all the other related concepts coming into the picture. So once you have continuous delivery model, then you build something called adaptive governance. So that means once you deploy the runtimes into the cloud, then you build some kind of observability, which includes matrix tracing, service visualization, and also you can get the feedback from the runtime and change the runtime behavior. So that is adaptive governance. So for example, let's say you have a service, microservice deployed into the cloud, and you are getting more traffic into that particular service. So then you dynamically scale it up, or you can scale it down. So that is adaptive governance. So a given cloud native application is actually consists of all these four different capabilities. Now, the role of integration in cloud native applications. So as we discussed earlier, a cloud native application comprises of multiple microservices, right? So that means when you are building a business use case, all these services has to talk to each other and formulate a given business scenario, right? So that's where cloud native applications, the services, the microservices or functions has to talk to each other, right? So once you decentralize, once you have a cloud native application comprises of multiple microservices, you will have a lot of inter-service communication, which happens over the network. So that's where all the integration capabilities are needed to build a fully fledged cloud native application. Now, we did the same thing in the service oriented architecture era, right? So we used to develop service oriented architecture as a set of services which are talking to each other over the infrastructure called enterprise service bus, right? So that's where all the business logic, so we develop most of the, so let's say you have set of application services, data and systems, and all the integration logic is being developed as part of the enterprise service bus, right? And also later after the advent of service-oriented architecture, the API management came into the picture, mainly to improve the usability or consumability of your business capabilities, because as you know, service-oriented architecture is really based on the standards such as web services, SOAP, WSDL, etc., which are not really easier to be exposed as a service to your consumers. Therefore, we usually put a facade layer, which is an API gateway or API management, which is a simple API to your complex system. So at that layer, you expose your capabilities to your consumers, and you can do versioning, throttling, security, observability. So, but at the ESP layer, we implement a lot of business logic, right? But with the advent of microservices architecture, what we are fostering is the elimination of the enterprise service bus. Now, if you try to eliminate enterprise service bus, what we are actually developing is smart endpoints and dump pipes. Right now, if we look at the previous architecture, we had a lot of business logic, inter-service communication logic as part of the ESP. Now we segregate that into microservices. Now, if you look at this diagram, you can see there are different types of microservices. You can see, for example, microservice A, E, likewise there are multiple microservices, and there are a set of microservices which we have labeled as smart endpoints, right? So a smart endpoint means the integration logic. So this particular smart endpoint contains the logic that talks to the microservices C and microservice D. So this is request response based communication, a sequential calls to two different other services. And with microservices architecture, also you can have asynchronous event-driven communication, which means you can use patterns such as pub/sub. Now, if you look at these two services, microservice E and D, so this is actually publishing data to an event bus, and there's a consumer who has subscribed to the same topic. Now, the concept of a smart endpoints and dump pipes is very important, because all the smarts, so in previous architecture, all the smarts live at the ESP layer. Now, in this architecture, all the business logic lives at the each and every microservice layer. And even the event bus scenario, there's no any business logic being developed as part of the event bus, but all the logic resides at the producer and consumer. Now, back in early 2000, we used to call this kind of an architecture, it's a point-to-point architecture, right? So you have actually this is the reason that we built ESP. So we used to have these point-to-point style communication between systems, and then we invented the ESP as the solution to eliminate the point-to-point connection between the systems. Now, are we going back to point-to-point integration? So that is the question, right? Not really, but we are trying to do a similar thing, but with microservices. But we need to eliminate all the mistakes that we did with point-to-point integration. Now, the key challenge in building microservices architecture is not just building the services, but building these smart endpoints. Because if you take 10 microservices, I would say 80% of the services will talk to other systems. So that means you are building smart endpoints with all those 80% of those services. So building smart endpoints is hard, right? Because ESP layers usually provide a lot of abstractions to make your life easier, right? Now, with the smart endpoints, with the microservices architecture, you need to implement all those capabilities as part of your services business logic. And integration complexity is not reduced, right? Although we don't have the central ESP, those complexity is not reduced, but rather it dispersed across the network with other set of microservices. And also, unlike service-oriented architecture, we have so many services now, right? Services are fine-grained, services are distributed across the network, and that means you will have more links between these services because of the inter-service communication. So the problem is even more harder. Now, I think it's in early 2016, the concept of service mesh has emerged. So actually, service mesh tried to eliminate some of the complexities that we have in this kind of inter-service communication in microservices architecture, right? So very early implementations of microservices architecture, they haven't used the service mesh concept. Rather, they built a set of fine-grained services, and they built inter-service communication between all these services. And what they have realized was there are a lot of commodity features that we need to implement at each and every microservice, right? So that means, let's take a scenario: you have a Go-based microservice and a Java-based microservice, and let's say a Node-based microservice. The same capability, things such as circuit breaking, observability, security, the same capability is being duplicated across these different languages. So that is and most of the developers are focusing more on building these links between services rather focusing on their business logic. So that's where service mesh came into the picture in early 2016 as a application network infrastructure to cater the inter-service communication. Now, with this architecture in this diagram, you can see two different microservices, microservice A and B, which are talking over the network. And with the service mesh architecture, you will have a separate sidecar component, runtime, co-located with your microservice, where you can offload your inter-service communication logic, right? So things such as circuit breaking, security, publishing data to external observability tools, those things are offloaded to the co-located sidecar. And all these sidecars are controlled by a central control plane, and this is where you push all your non-business logic related configurations to your services. And as part of the microservice development, you are only focusing on the business logic, and you will have some primitive network functions because you need to call the co-located sidecar. It's like a local host call to your sidecar, and all the other things are supported from the service mesh. So this architecture is becoming really popular, but again, one thing we have to realize is we will only offload non-business logic related configurations, right? You won't be developing any business logic related things inside the sidecar. So obviously, service mesh is not a distributed ESB. So many people have interpreted this as a distributed ESB, but it is not, right? Now, if you look at this particular scenario, you have a microservice X calling two other services over the service mesh infrastructure. Now, you have the business logic of the service, which contains microservice X calls service Y and Z, as well as the network communication logic. That composition logic is again part of the business logic of the service X, right? But all the other infrastructure related things are supported from the service mesh. Okay, so now it's clearly we need to have we have quite a lot of application integration requirements in building cloud native applications, right? So what we have marked here is the application integration that you developed as part of your service. So let's look at some of the key requirements that you need when you are building this kind of application integrations with cloud native or microservices architecture. So the first thing is whatever the runtimes that we are going to use for application integration needs to be cloud native, which means they should be startup time should be low, resource consumption should be low, and should natively integrate with Docker and Kubernetes and all the other Kubernetes or cloud native ecosystem components such as Prometheus and all the other tools. And there are two types of communication that you will implement as part of the application integration. So first one is service orchestration, the synchronous request response calls between services. Usually we call it the active compositions. Now if you look at microservice A, it calls two different other services, right? So this is one particular, because certain microservices requires request response style communication, whereas some services requires this kind of choreographic requirements, right? So usually in this case we have an event bus which is used as the dump pipe to connect different microservices. They are basically using produce and consume mechanism to communicate with each other. So in this case the business logic, in the previous use case you have all the business logic related to the composition as part of the microservice A. But in this case there is no central place that you will build the composition logic, because it is purely based on pub sub or that kind of messaging patterns. So usually this is implemented, the protocols such as REST, GraphQL, even gRPC is used for implementing this kind of active compositions, and choreography or reactive compositions are usually implemented with the messaging protocols such as NATS, Kafka, AMQP is heavily used. So another variation of the reactive composition is event sourcing. Probably you have heard of the concept of an event source. So the key idea behind event source is as part of the application or the microservice that you write, so all the state changing event of a given service is recorded in a distributed log, so that any other consumer of that events can recreate the state back, and they can actually materialize the behavior of the service that you have that is publishing the events. For example, this particular use case, I have an order management service publishing different states of the ordered states into a central distributed log such as Kafka, and all the other services subscribed can actually process the log and recreate all the events at this layer. So they can interpret these events differently, but everything is recorded in a distributed log. A slight variation of the same reactive composition is CQRS, command query responsibility segregation, because most of the services that you are developing are based on CRUD operations, right? So you do create, read, updates and deletes. But there are certain use cases that you need to treat reads versus writes differently, especially if your use case is write intensive. You need to use a different type of database for writes and different type of database for reads, right? For example, NoSQL for writes, RDBMS for reads. So in this kind of scenarios, you can split the query model, which is the write part, and the command model into two different services, and you can back those two services with completely different data stores and build an eventual consistency model between the data stores using some kind of eventing mechanism. Again, CQRS is another commonly used thing for specific use cases. So CQRS is not for all the microservices that you develop, but if your use case demands, you should use CQRS. So we talked a lot about different protocols, right? So building services means you are consuming and producing messages over a drastically different set of messaging protocols, right? Now usually you develop synchronous or request response services with protocols such as HTTP, gRPC, GraphQL, WebSockets and webhooks, whereas all the messaging, synchronous messaging is built using Kafka, Nets, AMQP. So likewise, there are a lot of protocols, which means the services that you are developing needs to understand these protocols, right? Which means when you are developing a service, you need to have sufficient abstractions from the underlying whatever the framework or the language that you are using to cater all these different protocols. For example, let's say you are building a microservice with C, right? So it won't be that easy, right? But if you are building something like a, let's say Go, you have much more higher level abstractions to implement using these protocols. So likewise, you should really concern about the underlying technology, because you have to cater different messaging protocols. And if you are coming from an integration background, the conventional or traditional integration background, you should be familiar with enterprise integration patterns. There are a set of patterns defined by Gregor Hope, which are mostly related to the service-oriented architecture, but most of them can be directly applicable for the microservices architecture as well. So things such as when you get a message, you can do forking, joining, splitting, looping, and different types of endpoints, aggregation. Those things are actually need to be part of your application development framework. So when you are building smart endpoints, you need to leverage these patterns. Resiliency. So we talked a lot about resiliency when you are using service mesh, but the reality is most of us are not using service mesh, right? Only very few, probably some tech companies use a service mesh, but most of the real world implementations are yet to use service mesh. So that means we need to have inter-service communication over the network, which is always unreliable, right? You cannot trust the network. And therefore, you need to have different resiliency patterns, such as timeout, retries, fail fast, bulkhead. So those kind of patterns has to be implemented as part of the service. So if the underlying framework provides an easy way to build a circuit breaker without writing any boilerplate code, then that's really great, right? So you need to look at these kind of resiliency patterns when you are selecting application integration or microservices development framework. And when we use inter-service communication, usually you have some messaging requirements, such as guaranteed delivery, exactly once delivery, at most once delivery. Likewise, different messaging delivery semantics. So based on the protocols that we are using, for example, if you are using AMQP, you get quite a few messaging semantics out of the box from the AMQP protocol itself. But if you are using something like Kafka, then you have to implement the message delivery semantics as part of the services that you are writing. For example, if you are using a Kafka producer and a consumer, at the consumer side, you need to keep track of the Kafka offset, right? The topic offset that you are consuming. And if your service goes down, you need to persist the offset so that you can read when you are up, when your service is up, you can read from where you left. So likewise, this delivery semantics has to be implemented as part of the service. And it's really great that if the underlying protocol, if the underlying framework provides these semantics out of the box. So microservices communication means, or composition means, we are dealing with a lot of message types, right? So types in the sense you have different types representation with different business boundaries. Right? So you represent a type with an employee, then you treat that as a student in some other cases. So likewise, there are different types, and as part of the service composition, you need to have some kind of a type mapping. So usually these types are directly mapped to the wire level protocols, such as JSON, XML, protocol buffers, or Avro. But when you are using things such as protocol buffers, these types are automatically coming into your service development framework, because you properly develop whatever the type that you are using, right? So for example, when you are using JSON, you may use something like JSON schema to define the types that you are using, but that is not really commonly used still. But when you are building services such as protocol buffers or gRPC, it is mandatory to define the types properly, right? So therefore you will get well-defined types as part of the service. And when it comes to complex type mapping, some organizations prefer to use this kind of a graphical tooling as well. So otherwise you have to do all this type mapping between two different types using programmatical approach. Basically you code all the type mapping logic, but certain integration solutions, almost all the conventional solutions provide this as a data mapping capability, but some of the cloud native solutions do provide the type mapping capability as well. Now if you look at the services that we are developing, the applications that we are building, we can categorize them into either of these categories, right? So usually most of the services that you developed are based on the API semantics, request response. Some services that you developed are based on event-based consuming, producing and consuming, and some are stream-based. Okay, so what are streams? Stream is another variant of events. So stream is a set of continuous set of events that you are processing. So usually when you are processing events, you will only process one event at a time and just complete it. But when you are processing a stream, you will process a sequence of events over the time. So when you are building this kind of microservices or cloud native applications, you may have to use some kind of a stream processing logic as well, right? So that's where things such as KSQL, there are a lot of other stream processing frameworks available. So if the use case requires stream processing, you need to select the underlying technology so that you have stream processing built into the underlying framework. And especially if you are coming from an enterprise background, you know that you are not in a green field, right? So you have to integrate with a lot of existing systems and services. So you need to have adapters for most of the existing systems, such as ERP systems, software as a service systems. So it's important to have all the required adapters and connectors from the underlying framework. Finally, the workflow requirements. So we usually talk a lot about stateless use cases, right? But in certain use cases, you have long-running processes which are stateful, right? So in those kind of scenarios, you need to implement business processes which are stateful, long-running, and also in certain scenarios, you need compensation and distributed transaction. So implementing distributed transactions with microservices is probably one of the hardest things, right? So that's where all the things such as the SAGA pattern, where you implement the distributed transaction as a set of compensation based states which are persisted into a distributed log. So with SAGA, what you can do is you can call multiple different microservices, and still you create some kind of a distributed transaction boundary between all those services, because you are actually persisting all the service calls into a distributed log. And if a given service fails, you can basically revert back the state using the compensation operations. Okay, so we talk a lot about the requirements that you have in building cloud native applications and building interconnection between those applications. So let's look at some of the cloud native frameworks that are available for doing this, right? So obviously, most of the conventional ESB solutions won't be a good fit for this, simply because they are monolithic, right? So they are not Docker friendly, they are not Kubernetes friendly. But some of the integration framework vendors, they have revamped their solutions so that we can map we can directly use them in a cloud native environment. So one of the best example is Apache Camel K. So Apache Camel is a well-known integration framework which is designed for monolithic architecture, but with Camel K they provided native integration with Kubernetes. So as part of the WSO2, we also used to provide a central enterprise service bus solution, but we built the micro integrator solution, which is the cloud native version. And if you are using Spring Boot, Spring integration will be a good candidate for doing this kind of application integration, because you get most of the required abstraction as part of the Spring integration. And also these application integration capabilities are baked into some of the frameworks, right? If you look at Spring Boot, you have things such as circuit breaker, and you have things such as retries. All those things are as packages in the Spring Boot framework itself. Vertex is very similar. Again, you have most of the abstractions built into Vertex framework. And there are certain programming languages. As I explained earlier, Go language has some of the abstraction required as part of the language. Node has those capabilities. And as part of WSO2, we have been also developing a new programming language called Ballerina, which is an open source language with most of the abstractions required to do integration. So for example, as part of Ballerina, you have you'll get first class constructs such as services, endpoints, circuit breakers, which are directly coming from the language. So you can give it a try. And also other frameworks are emerging, especially the Micronaut is Graal. It's a JVM framework based on Graal VM. So unlike Spring Boot, one of these Micronaut based instance will boot within few milliseconds, right? And I think Red Hat is working on something called Quarkus, which is again Graal VM based implementation of multiple things such as Camel, REST-DC, Prometheus. So it's kind of a combination of all those things running on top of Graal. So as part of WSO2, we are also trying to address most of the concerns that we have in this cloud native and integration landscape. So obviously Ballerina is a technology to develop these smart endpoints. So we have our conventional ESBs, the cloud native variant of that. And again, API management, we have a open, so all the WSO2 products are 100% open source. And our business model is based on commercial support. So you can try out some of these solutions to realize your business use cases. Okay, so in summary, application integration is not going away. So even if you use microservices or cloud native architecture, application integration could be the most important aspect to your architecture. So service mesh is it's becoming so popular. You can offload a lot of commodity. You can leverage most of the commodity capabilities from the service mesh, but it is not for application integration. And the good thing about service mesh is we are seeing most of the cloud providers now providing service mesh as a service. So for example, AWS or even GCP, they provide Istio or Envoy as a service from the underlying infrastructure. So it is becoming part of the infrastructure, which is great because we don't have to manage service meshes anymore. And it's very important to select the most appropriate technology to build your use case, to build your microservices use case. That heavily depends on most of the requirements that we just talked about. So based on the protocols that you are using, based on the messaging patterns you are using, you should select the underlying microservices development technology. Okay, so that's about it. So thanks for coming. So